Okay, so briefly, I don't want to spend all day on this because we've reviewed. If you're still having trouble with this, you should use the resources on 3/7. That was the date that I posted notes on balancing. Go to the Khan Academy videos, watch those, try to practice. If you still can't get it, stay after with me and we'll go over it, okay? So here's the answers briefly 16, 3, and 8. So 6, 1, 2, 1, 1, and 10, 2, 6, and 1. Okay, so let's just go over 2 and 4 just to save time. These ones I feel like point out to you some ways to make this a little easier, have fewer steps in your balancing process. So for number 2, for example, um, I've got imbalance in both the cesium and the nitrogen. Oops, I don't know what I'm doing there. Cesium, 3, and, okay. So you can see when I make my little table, I've got 1 cesium over here and 2 nitrogens. Come on, Jake. Head in the game. Cesium over here, there's 3 cesiums but only 1 nitrogen. So I've got imbalances on both sides. I could start on either side. However, it's going to be simpler for me. I'll have less steps if I start on the right or the left. If I start on the right with the more complicated thing, I'm going to have fewer steps, and here's why. When I change this, I change everything, right? I change cesium and nitrogen. But when I change one of these, I only change one element. Does that make sense? So I'm going to save those for last, and it'll make my life a little easier. Okay, so I want to change this coefficient to 2 so that I can balance the nitrogens. Now they're 2. And now I also have how many cesiums on the right-hand side? I have 6. So I have to go back here, and what do I put there? 6. And I'm finished. Is that okay? So I have fewer steps. If I start on the right-hand side, I just have 2 steps. It's a 2-step problem. Easy? All right. Let's look at 4. So number 4. We've got rubidium all by itself and rubidium nitrate. And we're making rubidium oxide and nitrogen gas. So here, I think the key is to make a table and recognize that on this left-hand side, I've got an odd number of oxygens. And what that means for me in my process is that probably best step is to make it even before I even start. So my first step is actually just to multiply right here by 2. That way I have 6 oxygens on the left. It's going to be easier to balance that because it's an even number. Does that make sense? So just by doing that, you're going to have fewer steps. This one's a 3-step problem if you do that first. If you don't do that first, it's more steps. Cool. All right. So that's my notes on that. If you're still struggling with that, please look at Khan Academy and catch yourself up. If you can't do that on your own, check in with me. Try to make an appointment after school. Okay. All right. So moving on. What we need to do now is called stoichiometry. And basically what we're interested in is being able to convert. Our goal for today is to be able to convert from moles, which you don't even know the definition of. We need to convert from moles to atoms. So obviously in order to do that, our first step is to define what a mole is. All right, so you've got two definitions that are of interest to me today. This one, Avogadro's number, and the mole. Those two are what we're trying to define. So I want you in your notebook, take out your notebooks, let's make a quick note. This right here is carbon, what you're looking at in this beaker, this is carbon-12. All right, this black substance is carbon-12. This is exactly 1 mole. So it weighs exactly 12 grams. So 1 mole is the amount of carbon-12 that weighs 12 grams. That's the definition you have up there. It's the amount of carbon-12 that weighs 12 grams. So let's think about carbon just as an atom for a second. What it looks like. How many protons do I need in order to make carbon? 6. So 1, That's hydrogen. See how it changes every time I add a proton? The element changes. Lithium, beryllium, boron, carbon. How many neutrons do I need to make carbon-12? 6. So 1, 2, 3, 4, 5, and 6. This is the most stable form of carbon. Notice it has a 1-to-1 ratio. It's the most stable form. And there's 12 things in the nucleus. 1 mole weighs 12 grams. Okay? So the amount of things in the nucleus relates directly to how much this stuff weighs. This is where the mass comes from. These particles, one of their properties is that they have mass. Okay? They're fermions as opposed to bosons, if you're interested in the physics, right? These ones have mass. So the number of massed particles in the nucleus affects how much it weighs. So as you move across the table from carbon to nitrogen, for example, if you had 1 mole of nitrogen, it wouldn't weigh 12 grams. How much would it weigh? 14.01 grams. Why 01? Isotopes, exactly. Because there's a little bit of nitrogen 15 out there, and that bumps the weight up a little bit. Make sense? Yep.
I thought you just said a mole was the amount of each element that equals 12 grams.
Not each element, carbon. So the definition I wrote on the board says the amount of carbon that weighs 12 grams is 1 mole. What if I had aluminum? If I tore off of this sheet exactly enough aluminum to weigh 26.98 grams, I'd have 1 mole. How many atoms of aluminum would that have in it? A lot. Billions. Billions and billions, right? So let's look at the exact number. I actually know the exact number. It's called Avogadro's number, because that's the guy who discovered it. And it is exactly 6.02 times 10 to the 23rd. Atoms. It's a lot. It's way too many to count. And that's why we're doing this. I mean, the point is, there are billions of atoms in this little beaker. That's more than I can count. Like, if we wanted to count that, it's more time than we have on Earth. So that would be counterproductive, right? We never make it through chemistry because we'd have to spend our entire lives counting how much carbon is in this beaker. Makes sense? So for time effectiveness, we're grouping them into moles so that we can count them easier. It's like if you were selling roses by the thousands. You wouldn't count them 1 rose at a time, you count them by the dozen. Right? It's a group that you can use to make it more efficient to count. Right? So if you had aluminum and you had 26.98 grams of it, that's 1 mole. That contains 6.022 times 10 to the 23rd atoms of aluminum. How many atoms are in this beaker? This is 1 mole. How many atoms are in here?
6.022.
Yeah, 6.022 times 10 to the 23rd. Is this a decimal?
Yes. Well, no,
Here's a number written out. Is that a decimal?
Yeah.
It's not. There's nothing after that decimal place.
No, that's a,
Why isn't it a decimal?
there's a lot of them.
You can't
have half a particle.
You can't have half a particle. You can't have half a particle. These are fundamental particles that make up the world, right? They can't be broken down anymore. Well, that's a lie. Actually, sorry. Specifically, protons are actually made up of quarks. There's 3 quarks. The problem is they really can't be broken down because when you do physics, at some point you'll learn if you try to separate 3 quarks, the amount of energy it would take to separate them put them infinitely apart would be an infinite amount of energy. So they really can't be broken down. But suffice it to say that these are the fundamental particles that make up the universe. They can't be broken apart anymore. So you can't have a fractional number of atoms. You just can't. Well, so that's why this number is not. This is not a decimal. Why does it say in scientific notation 6.022 times 10 to the 23rd? What am I doing there? It's scientific notation, and I'm keeping this amount of accuracy. How many significant digits are there? 4. Right? 6.022 here. Anyway, there's 4.
Okay, so that's just accuracy. We're keeping it to a certain amount of accuracy. This is really all we need to do really accurate work in the ladder, 6.022. There is more accuracy here, right? It goes 6.0221367. That's all the accuracy we have. We're just going to keep 4 of those. Okay, that's sufficient for our purposes. But it's not a decimal. It's a whole number of atoms. So what I want you to do right now is just take a look at this document, at this reading, okay, in your textbook. I want you to read from 320 to 322. But here's the trick. Here's the trick. When you're reading science, has this ever happened to you? You read a couple pages, you get to the end, you have no idea what happened. It just happened to Megan right now. I was talking, and all of a sudden she woke up, and she was like, wait, what happened, right? So the same thing can happen to you while you're reading. So how do you avoid that? You set a goal, and you check in with that goal. So our goal for today is to convert moles to atoms. So when you're looking at this document, this is your reading. When you're looking at this document, you should be checking in and saying, do I have a step-by-step method of going from moles to atoms? If that's your goal, you should be checking in with that comprehension and seeing if you're achieving it. Make sense? How often do you think you should check in? Like every paragraph, right? Every paragraph. Again, so that you avoid getting to the end of the page and going, I don't know what happened. I don't even know where I am. Does that make sense? Okay. So try that reading right now, and your goal is to, number 1, define the mole. Number 2, step-by-step procedure for converting moles to atoms. Got it? All right, give it a try.
Do we have homework also?
We do. The homework is at the bottom of that page I just handed you. I want you to do 4 practice problems. They are number 13, A through D, on page 324. Yep.
So, because instead of how they have weight specific elements.
Yep.
So that is how much.
Exactly, for each element. So the weight, what John's saying is this, it's periodic. There's a trend here. As you move across the periodic table, the weight of 6.022 times 10 to the 23rd atoms increases periodically. Right? As you move over from boron to carbon, the weight of the same number of atoms, 6.022 times 10 to the 23rd, goes up in grams. And it follows the periodic trend. Right?
More mass.
There's more mass in the nucleus, therefore it weighs more. Absolutely.